The method we just introduced works for finding absolute extrema on, again, closed intervals. So now what we want is a way to identify absolute extrema on other types of intervals, whether they're closed at one end, open at the other, open at both ends. How can we find absolute extrema for essentially any type of function? So what we're going to turn to is what's called the second derivative test. A few modules back, we introduced the first derivative test, where we looked at the first derivative, and that led us to some conclusions. So now what we're going to still look at is the first derivative, but add to that the second derivative to draw some conclusions about whether we have an absolute maximum or absolute minimum. So the second derivative test, works for any function f that's continuous on any given interval. So in order to apply, we want to first verify that our function is continuous on whatever that given interval is. So if we're considering from negative infinity to infinity, the function needs to be continuous everywhere. If we're considering from 0 to infinity, our function needs to be continuous on that given interval. So whatever we're considering in the function needs to be continuous. We need to find all critical values, which is again where our first derivative is equal to 0 or undefined. Then we're going to evaluate both the first and second derivative at each of those critical values. So this is where this method starts to change a little bit from the last one. Instead of evaluating the original function at critical values in the endpoints, now we're going to evaluate the first derivative and second derivative at those critical values. So if our first derivative evaluated at some point c equals 0, and the second derivative evaluated at c is greater than 0, then that point c is an absolute minimum. If the first derivative evaluated at c equals 0, and the second derivative evaluated at c is less than 0, then c is an absolute maximum. So let's pause before we introduce this last step just to kind of identify why those conclusions are leading us to those results. So if we have, let's consider step 4 here first. If we have some given point, we know the derivative there is 0, which means we have a horizontal tangent line at that point. And we know that our second derivative is positive. That means this has to be concave up around that point. So without knowing specifically what our function looks like, we have something like this. We have a curve that's concave up. We have a horizontal tangent line, which makes this point a minimum. Looking at step 5 here, or that second case, if we're given a point and we know that the first derivative is equal to 0, again, that's telling us that we have a horizontal tangent line. And we know that our second derivative is less than 0, it means that our graph is concave down. So our curve is that upside down bowl shape. Then we have a horizontal tangent line, but we have to continue in that concave down shape. So this means we have an absolute maximum. So that's why we're looking at the first derivative and second derivative and comparing those results to 0, because they're giving us one of these two general pictures. And then our third case to consider here is if the second derivative evaluated at c equals 0, then the test is inconclusive. So all we would know in this third case is that we have some point. We know that we have a horizontal tangent line, but evaluating the second derivative and getting 0 doesn't tell us anything about the concavity of the function. So we don't know which way this function is curving. We don't know anything yet about if it's increasing, decreasing. So there are two cases where the second derivative test gives us immediate results, and we can classify points as an absolute minimum or maximum. But we have this third case where the second derivative test essentially fails, or at least fails to give us any conclusive result. So if the second derivative test is inconclusive, then what we have to do is go back to the first derivative test that we introduced in module 7.1. So when we have this last case to consider, we already know that we have a horizontal tangent line here, so we would go back to the first derivative, and we would again look at constructing a sign chart to say that we know on one side that's negative, on the other side it's positive, and that would tell us that our graph is decreasing and changes to increasing, so we'd have an absolute minimum. Again, if our first derivative sign chart turned out a little bit differently, we could have an absolute max, we could have neither. But in the case where the second derivative test is inconclusive, so whenever the second derivative evaluated at this point C gives us a 0, then we have to go back to the first derivative test in order to classify that point as an absolute maximum or minimum.